We'll check by addition when we're done. 900 minus 6.1. Well, that's 900.0 minus 6.1. Borrow. These zeros become nines. 9 becomes an 8. 10 minus 1 is 9. 9 minus 6 is 3. 9 minus nothing is 9. 8 minus nothing is 8. 893.9. And if we add the 6.1 to the 893.9, we get 900. So we got the right answer, 893.9. So because of the fact that the decimal points need to be lined up, and it's not always going to match up with the same number of digits, that means that there will often be cases where we are filling in missing zeros. And that means that there's going to be a lot of subtraction work that has to do with borrowing and zeros. So if that was a struggle with subtraction for you, that struggle is going to become real. So you'll be able to say the struggle is real. Let's look at this one. 8 minus 0.0023. When we line it up, that would be 8 point. We need 4 of them. 0000 minus 0.0023. Why did I put all those in there? Because 8 minus this decimal, the decimal has to line up, which means it's 8 point. And because of all these blank spaces, I need to fill them with zeros, which means the subtraction is going to be involving 0. But we're going to borrow. 8 becomes a 7. All the skipped zeros become 9s, and that 0 becomes a 10. 10 minus 3 is 7. 9 minus 2 is 7. 9 minus 0 is 9. 9 minus 0 is 9. Decimal point. 7 minus nothing is 7. And if we add the 0.0023 back, we get 0, 0, carry the 1, carry the 1, carry the 1. We get 8. 7.9977 is correct here. We checked by adding. We got the right answer. Our favorite type of subtraction, word problem. Subtract 7.3 from 16. Same as before. When we're subtracting something from something else, we have to think it through. What are we starting with? We're starting with the 16. We are subtracting 7.3 from that. And notice how I set it up. Since 16 would be 16 point, that lines them up. Fill in a 0. Subtract, borrow. 10 minus 3 is 7, decimal point. 5 minus 7 can't do it. Borrow. 1 becomes a 0. 5 becomes a 15. 15 minus 7 is 8. And if we check by adding, 8.7 plus 7.3 is 16. Got the right answer. 8.7 is it. If we're adding 3 decimals, just like adding 3 whole numbers, we write them vertically and add. The only difference is we need to make sure to line up the decimal points. So insert a 0 after the 0.23. So we have 0.230 after the 756. Everything else had 3 decimal places. The decimal points line up. We're able to add. 0 plus 4 is 4, plus 7 is 11. Put down the 1, carry the 1. 1 plus 3 is 4, plus 8 is 12. Put down the 2, carry the 1. 1 plus 2 is 3, plus 5 is 8. Decimal point lines up with the decimal point in the problems. 6 plus 6 is 12, plus 1 is 13. Put down the 3, carry the 1. 1 plus 5 is 6, plus 2 is 8. And then 7 is just 7. 783.821. 783 and 821 thousandths. 19 plus 26.072. We want to write 19 so that it has 3 decimal places, so that we have the same number of decimal places in each number. So 19 becomes 19.000. We're adding 26.072. Add like normal, putting a decimal point in the answer in the same spot as it is lined up with the decimal points in the problem. 45.072. 45 and 72 thousandths. We treat adding with negative numbers the same way that we would with regular integers. We're adding 2 numbers with different signs. The sign of the larger absolute value is negative, so our answer overall will be negative. We have to do 9.92 minus 7.12. That gives us 2.80, and the sign will be negative, so negative 2.8. We don't need that 0 at the end. $56.21 minus 5.9. When we write that and line up the decimals, we'll need an extra 0 after the 5.9. And this is a standard subtraction problem involving borrowing. 1 minus 0 is 1. 2 minus 9, can't do it. Borrow 1 from the 6, turning it into a 5. The 2 becomes a 12. 12 minus 9 is 3. 5 minus 5 is 0. And the 5 is just a 5. 5 minus nothing is 5. So 50.31. 50 and 31 hundredths. $28 minus 3.3. Again, put in a 0.0 after the 28. We're lining up the decimals. We're filling in any empty spots with zeros. Subtract 0 minus 3, can't do it. Take 1 from the 8, that turns it into a 7. That 1 turns the 0 into a 10. 10 minus 3 is 7. 7 minus 3 is 4. 2 minus nothing is 2. 24.7. 24 and 7 tenths. In words, subtract 19 from 25.91. Subtract 19 from 25 and 91 hundredths. When we're subtracting something from something else, we're starting with that something else. We're starting with the 25.91, and then we're subtracting 19 from that. This would be 25.91 minus 19. Give ourselves a decimal point and 2 zeros to line everything up. Subtract like normal. We end up with 6.91. 6 and 91 hundredths. Negative 5.4 minus 9.6. Subtracting is adding the opposite. So this is adding two negative numbers. If we're adding two negative numbers, the common sign is negative, so our answer is negative. We'll need to add 9.6 and 5.4. That gives us 15, so our answer is negative 15. When we line up the decimal points and add, we get 15.0, and we don't need the 0.0. Negative 1.05 minus negative 7.23. Subtracting is adding the opposite. The opposite of a negative is positive. So we are adding a positive. This is negative 1.05 plus 7.23. Or we can think of those two subtraction bars coming together to form an addition symbol. Adding two numbers with opposite signs. The larger absolute value is the 7.23. That one's positive. So our answer overall is positive. 7.23 minus 1.05 is 6.18. Estimating when adding or subtracting decimals. To help avoid errors, we can estimate to see if our answer is reasonable by rounding the given numbers and adding or subtracting. For example, 7.6 minus 2.1, the exact would be 5.5. Rounded, 7.6 rounds to 8, 2.1 rounds to 2. 8 minus 2 is 6. 6 and 5.5 are close. So this is a reasonable answer. But checking like this helps us avoid decimal mistakes. What if we accidentally put the decimal point in the wrong spot and get 55 or 0.55? Well, 0.55 and 55 aren't close to 6, so it would be an indicator that we did something wrong. This is more useful when it comes to multiplying or dividing. It's very hard to screw up, keep the decimal point in the same spot and line them up. That's what we do with addition and subtraction, but we don't do that with multiplication and division. So it's harder to keep track of where the decimal point is in those other operations. But let's use estimation and give ourselves a check on 23.8 plus 32.1. 23.8 rounds to 24. 32.1 rounds to 32. When we add the exact, we get 55.9. When we add our estimate, we get 56. Those are close, so this is a reasonable answer. Evaluate x plus y for x equals 5.5 and y equals 2.8. What do we do? Plug it in, plug it in. Plug in 5.5 for x, plug in 2.8 for y, and we have 5.5 plus 2.8 instead of x plus y. This is 8.3. Line up the decimal points, add, carry the 1, 8.3. So we're just doing everything we've done so far, but we're involving decimals. Simplify by combining like terms. Negative 4.3y plus 7.8 minus 20.1y plus 14.6. We can move the terms around so that our y's are next to each other and our constants are next to each other. Be sure that when that 20.1y travels, that it travels as the negative 20.1y that it is. The sign in front is attached. So we have negative 4.3y plus negative 20.1y. Adding two numbers with the same sign, common sign is negative, we're going to get a negative answer. Negative 4.3 of them plus negative 20.1 of them. We would add those numbers and get 24.4. So negative 24.4y. And then 7.8 plus 14.6 is 22.4. So negative 24.4y plus 22.4. We don't add those numbers together because those are not like terms. Y's can only be added with y's. Constants can only be added with constants. Find the total monthly cost of owning and operating a certain automobile given the expenses shown. The monthly car payment, $563.52. The monthly insurance cost, $52.68. And the average gasoline bill per month, $127.50. We want to add these three things together to get the total monthly cost. Line up the decimal points and add. $563.52 rounds to 600. $52.68 rounds to 50. $127.50 rounds to 100. That's about 750. And when we actually add, we get $743.70. The estimate is close. This is a reasonable answer. The total monthly cost is $743.70. The bar graph shows the average heights for adults in various countries. How much greater is the average height in the Netherlands than the average height in Czechoslovakia? Well, in the Netherlands, the average height is 72.6 inches. In Czechoslovakia, the average height is 70.8 inches. To find how much greater the one is than the other, we would subtract the two. So 72.6 rounds to 73. 70.8 rounds to 71. That's an estimate of 2. We get 1.8. So we have a reasonable answer. The average height is 1.8 inches greater. And that's it for this topic. The topic is multiplying decimals and circumference of a circle. The objectives in this topic: multiply decimals, estimate when multiplying decimals, multiply decimals by powers of 10, evaluate expressions with decimal replacement values, find the circumference of circles, and solve applications by multiplying decimals. So multiplying decimals is similar to whole numbers. The only difference is that we place a decimal point in the product. So when we added or subtracted, we had to line up the decimal points. We don't do this when we multiply. We don't want to, we'll get the wrong answer. So multiply the decimals as though they are whole numbers. The decimal point in the product is placed so that the number of decimal places in the product is equal to the sum of the number of decimal places in the factors. So look at the numbers you're multiplying, count how many decimal places there are total, and that's how many decimal places will be in the answer. So for example, 0.7 times 0.9, the decimal points just happened to line up. We didn't do it on purpose. That's okay. This is the same as 9 times 7, so that's 63. And there are a total of 2 decimal places in the problem. So we write our answer with 2 decimal places, 0.63. Notice the decimal point does not line up with where it is in the problem. That's okay. That's expected. That's wanted. 0.63 or just 0.63. So for multiplication, you are going to forget about the rule of lining up the decimals. Okay, lining up the decimal points, that is just addition and subtraction. Multiplication and division, you set them up just like a normal problem. So let's say we had 2.31 times 9.4. Ignore the decimal points. Just ignore them entirely. If it was 231 times 94, we would just set it up like this. So that's what we do. Notice the decimal points are not lined up. Do not go out of your way to line them up. If they happen to line up, they happen to line up. But that does not mean that that's where the decimal point will be in the answer. We'll get to where the decimal point will be in the answer after we're done multiplying like normal. 4 times 1 is 4. 4 times 3 is 12. Carry the 1. 4 times 2 is 8, plus 1 is 9. Moving over to the 9. 9 times 1 is 9. 9 times 3 is 27. Put down the 3, carry the 2. 9 times 2 is 18, plus 2 is 20. And then we add. 4 plus nothing is 4. 2 plus 9 is 11. Carry the 1. 10 plus 7 is 17. Carry the 1. 1 plus 0 is 1. 2. Now the answer is clearly not going to be 21,714. In fact, if you look at the numbers we multiplied, 2.31, that's about 2. 9.4, that's about 9. So 2 times 9, that's about 18. So 21,000 doesn't make sense. 2,171 doesn't make sense. 217 doesn't make sense. 21 is awful close to 18. That's the closest. In fact, we'd expect it to be there based off of estimating that that's about 9, and that's about 2, and that's about 9. So the answer will be about 18. Here's how we find where it goes. How many decimals or how many places after the decimal points did we have in the original problem with both numbers? 1, 2, 3. There were 2 after with this one. There was 1 after with this one. 2 plus 1 is 3. So the answer needs to have 1, 2, 3. Sure enough, that decimal point does go there. And the answer is 21.714. Let's do another. Let's take a look at 0.194 times 0.7. 7 times 4 is 28. Carry the 2. 7 times 9 is 63. Plus 2 is 65. Carry the 6. 7 times 1 is 7. Plus 6 is 13. Carry the 1. 7 times 0 is 0. Plus 1 is 1. And then here, 0 times everything would just be 0. Add 8, 5, 3, 1. And count 1, 2, 3, 4 digits past decimal points. 1, 2, 3, 4. So the point would go here. We can have our 0. Our answer would be 0.1358. Now, when you're doing this, taking into account that zeros in front of the decimal, if that's all that's there, remember they're not needed. We could just do 194 times 7, have our decimal points there, and just do this work. 7 times 4 is 28, 63, 65, 13, 1, 2, 3, 4, 1, 2, 3, 4, 0.1358. If you so choose, you can put a 0 in front. Take a look at this one. 492.8 times 0.065. 5 times 8 is 40. 5 times 2 is 10. Plus 4 is 14. 5 times 9 is 45. Plus 1 is 46. Carry the 4. 5 times 4 is 20. Plus 4 is 24. Done with those. Moving on to the 6. 6 times 8 is 48. 6 times 2 is 12. Plus 4 is 16. 6 times 9 is 54. Plus 1 is 55. 6 times 4 is 24. Plus 5 is 29. We could do 0 times all of that. We could do 0 times all of that, or we could just ignore that we have these zeros and move on with our day, as it were. Four plus 8 is 12. 13, 10, 12, 3. So it looks like Before we put the decimal point in, we have 320, 320. Where does the decimal point go? What's our last step? What's the new thing for multiplying decimals that we didn't do before? It's the counting 1, 2, 3, 4. The counting of how many places we have to the right of decimal points. So 1, 2, 3, 4. 1, 2, 3, 4. 32.0320 would be the correct answer here. So addition and subtraction. Line up the decimal points, add or subtract like normal. Multiplication. Do not line up the decimal points. Multiply like normal, and then do that counting at the end to figure out where the decimal point goes. Division, that's going to have its own set of rules. But before we get there, now that we've talked about how we should not line up the decimal points, I did mention sometimes they do happen to line up on their own. And that's okay. But that does not mean that the decimal point is in the same place in the answer. For instance, if we had 2.3 times 3.1, look, the decimals just happen to line up. And that's okay. But where is the decimal point going to be in the answer? 2 spaces over, because of these 2 spaces total past decimal points. 1 times 3 is 3. 1 times 2 is 2. 3 times 3 is 9. 3 times 2 is 6. Add 3, 1, carry the 1, 7. But it's not 713. It's 7.13. Okay. So I mentioned when we were talking about addition and subtraction and estimation that estimation would be far more useful in multiplication. Once again, though, we can estimate to check for reasonableness. For example, if we had to multiply 5.3 and 4.2, 5.3 rounds to 5, 4.2 rounds to 4. The estimated answer would be 5 times 4, or 20. When we multiply this out and we get 2,226, and then we count that we need 2 decimal places, and we put our 2 decimal places in, we get 22.26, which is close to 20, so our answer is reasonable. But checking the estimate is a protection against putting the decimal point in the wrong spot. If we accidentally did 2.226 or 222.6, we would notice that 2 and 222 are not close to 20, and that we likely screwed up somewhere. But since we got a close answer to our estimate of 20, we know it's reasonable. Let's multiply 32.3 times 1.9. We'll do exact, we'll do estimate, we'll make sure that we're close. Exact would be 32.3 times 1.9. 1 decimal place from the first number and 1 decimal place from the second number. Give us 2 decimal places in the answer. 61.37. Feel free to multiply that out by hand to check that. You can pause. There's nothing stopping you from pausing and checking and working on your own. The estimate would be 32 times 2, which is 64. which is close to 61.37, certainly closer than 6 or 613. So this is a reasonable answer. There are some patterns that occur when we multiply a number by a power of 10, such as 10, 100, 1,000, 10,000, and so on. And that pattern has to do with the number of zeros in the power of 10. 1 0, 2 0, 3 0, 4 zeros, and so on. When we multiply by powers of 10 that are greater than 1, we move the decimal point to the right the same number of places as there are zeros in the power of 10. So times 100 would be moving 2 to the right. 2 to the right because of the 2 zeros in the 100. Now, if we're multiplying decimals by powers of 10 less than 1, such as 0.1, 0.01, 0.001, etc., we move the decimal point to the left the same number of places as there are decimal places in the power of 10. So not zeros anymore, but decimal places. 0.006 times 0.01. Let me say that again in case I screwed that up. 0.06 times 0.01. There are 2 decimal places in the 0.01. That's less than 1, so we're going to the left. And from 0.06, we go left 1, 2 to get 0.0006. Three 3.4305 times 100 times 100 greater than 1, 2 zeros. Decimal point goes 2 to the right. 1, 2, 343.05. $76.543 times 10, 1 0. The decimal point moves 1 to the right. 765.43. Times 100, that's 2 zeros. 7,654.3. Decimal point moved 2 to the right. Let's kick it up a notch. Times 100,000. That's 5 zeros. So the decimal point would move 5 to the right. 1, 2, 3, 4, 5. 7,654,300. The decimal point is moved the same number of places as there are zeros in the power of 10. So we're driving that point home. We did that with the positive powers of 10, the powers of 10 greater than 1. Let's do some extra practice with those powers of 10 that are less than 1, 0.1, 0.01, 0.001, etc. We move to the left the same number of places as there are decimal places. $8.57 times 0.01. 2 decimal places in the power of 10. Less than 1. Move 2 to the left. We're going to have to add a 0 to the left of 8 to make this work. 1, 2. 0.0857.
So we're going to be moving decimal points to the left or to the right a certain number of spaces in A, B, and C. In A, we're multiplying by 0.01. That's less than 1. There's 2 decimal places, so we're moving the decimal point 2 to the left. 0.581. 581 thousandths. In B, we're multiplying by 0.1. That's less than 1 decimal place. We're going to move the decimal point 1 to the left. Right now, we imagine it's after the 4. We're going to move it so it's between the 2 and the 4. 8,562.4. And then in C, we're multiplying by 100. That's greater than 1. There are 2 zeros. We're moving 2 to the right. The decimal point moves from where it is to between the 0 and the 6. 2,410.6. Evaluate 7y for y equals negative 0.028. Plug it in, plug it in. 7 times y becomes 7 times negative 0.028. Be careful that you don't subtract here. This is not subtraction. That negative sign isn't before the parentheses, it's inside of it. This is multiplication, 7 right up against parentheses. Positive times negative is negative. If you multiply 28 times 7, and then write your answer so that there is a total of 3 decimal places, we get negative 0.196. So something we've dealt with in the past was the distance around a polygon, and we called it the perimeter.
What about this bad boy right here? How do you suppose we deal with that? Perimeter is add the sides. Well, a circle is one big side that really never ends. It comes back on itself and it just goes on and on. So we have special words for perimeter and area. We call the perimeter the circumference. circumference. We call it the circumference. And we call the area the area. Area is still area, but for a circle, the perimeter is actually the circumference. The formula for the circumference is this. And now you've just dropped over. What am I doing? This is the Greek letter pi. Pi is approximately wavy equal sign 3.14. If you want to get more specific, it's approximately 3.141592653588979, and then it just keeps going and going and going. Pi never ends, and it never starts to repeat itself. 3.14 is a common approximation that you'll see for pi, but it is not going to give you an exact answer. Not exact because it's not exactly 3.14. It's all that. So March 14th, that's why that's called Pi Day, 3/14. It's not eating pie, which you might do on Pi Day, but it's about this pi, the mathematical pi. So the circumference, the distance around the circle, equals pi times the diameter. Well, what's a diameter? That's another new word. A diameter, now I've drawn a Pokeball. The diameter is the length of the circle at its biggest point. So not that, that would not be a diameter. Halfway down. Splits it into 2 equal parts. This would also be a diameter. 2 equal parts. These 2 diameters cross each other. That's 4 equal parts. But anything that goes from one end goes through the center of the circle, that's a diameter. Full length. We have a special word for half of a full length as well. Very important word when it comes to area. We use the letter R for radius. R equals the radius. And what is a radius? It's half of a diameter. A diameter divided by 2 will give you the radius. And the area of a circle is pi times the radius squared. Since 2 radiuses, the plural, by the way, is radii, since 2 radii make up a diameter, another formula you'll see for circumference sometimes is 2 pi r, because 2 times the radius, 2 radii, make up a diameter. So this is the same as pi times the diameter. So now here we are with 2 formulas, one for circumference of a circle, one for area of a circle. And all you need to solve either of them is a radius measure. If you have the radius measure, you can find an approximation by using 3.14 for pi. Or you can just keep pi and get an exact answer, right? Okay, so we have a circle. The circle has a radius of 6 meters. We're going to find the circumference in terms of pi. In terms of pi means we want an exact answer. Do not replace pi with 3.14. So the circumference is going to be 2 times pi times r. So 6. And 2 times 6 is 12. So we have 12 times pi. 12 pi right next to each other means times. That makes sense. If 6 is the radius, then the whole diameter would be 12. Pi times the diameter, 12 times pi. Since it's just distance around, not stuff inside, it's still going to be meters, not meters squared. Meters squared, that's going to be for area when we multiply meters times meters. So 12 pi meters would be the exact answer here. Now let's also find an approximation. For an approximation, we just continue. And now instead of pi, we're going to replace it with its approximation 3.14. And we multiply 3.14 times 12. That's why we've waited until now, because we need to know how to multiply decimals. 2 times 4 is 8. 2 times 1 is 2. 2 times 3 is 6. Move over to under the 1. 1 times 4 is 4. 1 times 1 is 1. 1 times 3 is 3. Add 8, 6, 7, 3, 2 places past the decimal. Whoops. So 37.68 meters would be an approximation, not exact. Exact would be 12 pi, but 37.68 meters would be the distance around this circle, the perimeter, but it's special word, the circumference, because it's a circle. Makes it special. What do you think? You're some type of circle? Okay, let's do it again. This time our circle is 5.2 yards for a radius. Let's find an exact circumference. Let's then do an approximation. If 5.2 is the radius, that means we have 2 times pi times 5.2. 2 times 5.2 is 10.4. So 10.4 pi is the circumference, and that's in yards. How would we get an approximation? Well, we would replace pi with 3.14 and then multiply 10.4 times 3.14. 4 times 4 is 16, carry the 1. 4 times 0 is 0, plus 1 is 1. 4 times 1 is 4, and then 1 times everything. 4, 0, 1. And 3 times everything. 3 times 4 is 12, carry the 1. 3 times 0 is 0, plus 1 is 1. 3 times 1 is 3. I forgot to move over. 3 times everything. 3 times 4 is 12. Carry the 1. 3 times 0 is 0. Plus 1 is 1. 3 times 1 is 3. We add 6, 5, 6, 2, 3. And 1, 2, 3 decimals, places after the decimal makes this 32.656 yards.
So an example problem, find the circumference of a circle whose radius is 4 inches. If the radius is 4, And the circumference is 2 times pi times 4. 2 times 4 is 8, so 8 pi inches. That would be an exact circumference in terms of pi. If we want a decimal approximation, we would replace pi with 3.14. So the circumference of 8 pi is approximately 8 times 3.14, and that gives us 25.12 inches. 25.12 inches would be the approximate circumference of the circle. Let's find the circumference of a circle with radius 9.1 yards. 2 times pi times r. 2 times 9.1 is 18.2. 18.2 times 3.14 is 57.148 yards. So a new formula that we know.
You may have heard something like this before, 1.6 billion. Well, do you know what that means? We can use the decimal point as a sort of time saver when saying really large numbers that have a lot of zeros in them. 1.6 billion would be 1,600,000,000. And that's it. 1,600,000,000 is how you say this really long number, because this grouping is ones, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions. Since this first comma is a billion, if we replace it with the decimal point and erase all of the zeros at the end, we can just say that. So instead of 1,600,000,000, we can just go 1.6 and get rid of all those zeros. And what was that comma? It was a billion. 1.6 billion. So we can write really large numbers like that. How about 46.4 million? How would we write this as a number? Well, thinking about that logic, if this point is here, that means it's where the millions would be. So it should be 46 million and then a 4. The rest would be zeros, but if this is 46 million, that means that 4 has to be 100,000. So 46,400,000. Now that we know everything we need to know about multiplying decimals, when we multiply length times width, what is that? That's area of a rectangle, length times width. If we had a square, what makes a square and not just an ordinary rectangle? Because we could still do length times width to get the area, but it's that all the sides are the same length. So for a square, you just have one side length, and that's all 4 sides. So for perimeter, you would multiply the side by 4, because that's the same as repeatedly adding that plus that plus that plus that when all 4 are the same thing. So the area of the rectangle formula tells us that an area of a square would be side times side. What do we call it when we multiply something by itself? We call it squaring. Side times side is side squared. Side what? Squared. Area of a square. 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 That's where that comes from. Remember, I showed you how area is all the different 1x1 squares you can fit on the inside of a thing. So why are we waiting until now to talk about how the area of a square is just side squared? Well, because measurements are not, they're not unique. They're not always going to be, exactly 3. When you take a measurement of something, you're going to get 3.1. You're going to get 4.7. You're going to get 129.03. So you're not always going to be working with whole numbers. In fact, you're rarely going to be working with whole numbers. So let's say we have a square. And the side of this square is 2.3 meters. What is the area of the square? So we would multiply 2.3 times 2.3 because this would be 2.3 squared. 2.3 times itself. 2.3 times 2.3. 3 times 3 is 9. 3 times 2 is 6. 2 times 3 is 6. 2 times 2 is 4. Add 9, 12. Carry the 1. 1 plus 4 is 5. 2 decimal points, or 2 places past the decimal point. 2.3 squared is 5.29. And in this case, we would have meters squared as well, or squared meters. Let's say the area of the square was just, or the side of the square was just 0.3 meters. Or 0.3 meters, same thing. Well, 0.3 times 0.3 is not 0.9. 3 times 3 is 9, but notice 2 spaces past the decimal. So 1, 2 spaces have to be there. So the area would be 0.09 square meters. So for the area of a rectangle, you do length times width. And then if it's a square, that becomes side squared, but it's still length times width.
And now for something completely different. Jose Severos, an electrician for Central Power and Light, worked 40 hours last week. Calculate his pay before taxes for last week if his hourly wage is $13.88. So $13.88 per hour for 40 hours. That's multiplication. Multiply 1,388 times 40. We get 55,520. And then we need to put a decimal point in there. The original problem had 2 decimal places, so we need 2 decimal places in our answer. 555.20. $555.20. And that's it for this topic.